Up to now, chapter 3 is rather abstract when it comes to the description of univariate and bivariate properties of random variables. Now I would like to go more to an application of that theory to hydrological variables. And the field that is focused on the application of statistical, especially random variable theory to hydrological variables is called hydrological statistics. And it's mostly concerned with extremes, as you will see. So for instance, in this particular lecture, we're going to look particularly at the discharge time series that are observed at Lobit here. That's the Rhine. And the Meuse, or Maas in Dutch, that enters the Netherlands here at IJsden, just south of Maastricht. So today we're going to look at the Rhine, and in our practical next Thursday, you can do everything yourself using data from the Meuse. So hydrological statistics is concerned with the statistics that describe the behavior of hydrological time series. These could be discharges, groundwater, any of those. So it can describe the mean behavior, like the probability distribution, the variance, the cumulative probability distribution function. But it often concerns also the, and mostly it is concerned with the statistical analysis of extreme values, because those are the most interesting, the floods and the droughts. And that is what we're going to look at today. So this is the discharge from the Rhine. You can get it actually from any from GRDC. This is the global runoff data center. Has discharge time series, monthly time series for many of the global rivers in the world. But you can also get the daily ones from the Rijkswaterstaat sites. And you can see it's quite it changes quite rapidly from very low discharges in certain years, but also there are some spikes, and the highest one was actually in 1926, more than close to 14,000 cubic meters per second. So there's a huge range in there, and you can portray that in very, very many different ways. You can actually pick out a given year. For instance, this is the year 1952. Or we can look at every month what the distribution of Rhine discharges, and you can see these are box and whisker plots of every month. And typically you can see there's lots of data that are outside the whisker on the upper side, so it's actually very skewed distribution. And normally one would call these outliers, but we're really most of the times interested in that. Another way of describing the behavior of a river or a time series is looking at the flow duration curve. And that's how hydrologists often like to look at hydrographs, by turning it into a flow duration curve. It's basically the same as calculating the cumulative frequency distribution of data, but it's a little bit reversed. It's not about the probability that something is lower, but the probability that it's higher than a certain value, and also the probability is on the x-axis and the value is on the y-axis. So what you can here see that 40% of the data has 40% of the discharge days have a discharge larger than, say, 2,100 cubic meters per second. Yeah. And 20% of the days, if these are daily data, have a discharge larger than 3,000 cubic meters per second. So this is how it's done. Yeah. Now, hydrological statistics of extremes is particularly interested in these extreme values. Yeah. So this part of the flow duration curve, and in the box plots the outliers here. Those are the ones of interest. So, of course, this is not only the case for discharges, but you can do this for many hydrological interesting data, such as rainfall, wind speed, sediment content, concentrations of some pollutant, and so on. So why are the statistics of extreme events so of interest? Well, of course, if you want to prepare yourself for disasters, you want to know what the probability is that a certain event of a given large size occurs. And so that's one question we would like to ask. So what's the probability that the discharge in the Rhine will be larger than 16,000 cubic meters per second? Because that's basically one that could cause flooding. But also, if you design the dikes of a certain height, the dikes need to withstand a certain event. They are designed based on a certain event, and this event is given by a certain design frequency. For instance, the dikes in the western part, the sea dikes in the Netherlands, are designed to withstand a flood that on average occurs once every 5,000 years, for instance. Yeah. So how high then is that event? What is the river level? What is the sea level? Or when it comes to river dikes, what's the discharge that belongs to this design event? And that is what hydrological extremes or hydrological statistics tries to figure out. So there's two ways of selecting what a maximum or extreme is. One is the so-called yearly maxima method. So you have a year, these are calendar years, but sometimes people use also hydrological years. So they start from April 1st until April 1st the next year. That's especially in the northern hemisphere, where most of the floods occur in winter, because precipitation is because evaporation is low, so there's lots of runoff, and there can be snow melt in early spring. Anyway, this is done in calendar year, so this is the maximum event in 1991, 1992, 93, 94, 95. This was actually an extreme event, an extreme flood, and so on. Yeah. So after doing that, yeah, you have a collection of maxima that you then analyze. Another way of doing it is the so-called peak over threshold method. They're also called partial duration series. Is that you take a certain threshold that is high enough, can be actually quite arbitrary what this threshold is, but it should be high enough for the events to be extraordinary, and then you take all the values that are higher than that event and analyze these. By the way, this can also be a natural boundary. For instance, if this is the height of the natural levy of the river, for instance, that would be a natural level, and then you have actually all these peaks over threshold that occur are actually natural floods. Yeah? That's one way of doing it. Now, in in our analysis, we're only using the first part. But if you want to see how the analysis goes for these peak over threshold data, I refer to chapter 4. There's also a part on POT data in the reader. Okay. So we go first to the first one. We have these maxima. Once we have that, we do that for our Rhine time series, and we have here 120, as you can see, from 1900 until 2019, maxima for the river Rhine. And you can see the very high ones in 95 and 96, and the extremely high one in 1926. So these we are going to analyze. And to analyze these, we have to make some assumptions. First of all, we assume that all these maximum values are realizations of independent random variables. So the value of the maximum of 1992, it doesn't depend on the maxima in any of the other years. Yeah? So there's independence. And they occur random. So we assume that some mathematical model, there's some random process that generates these maxima. There's no trend. So we have to assume that the series is what is called statistically homogeneous. So there's no trend or any change both in the, there's no trend in the maxima. Yeah? So we have to assume that the maxima are, the probability of a certain maximum is the same in 1900 as it was in 2015. And these maximum values are identically distributed. So they are basically coming from the same underlying probability distribution. So if it were discrete, they would basically be coming from rolling the same dice many times, right? So in this case, we can fit a single probability distribution to these maximum values and use that to extrapolate our observations to see what is the probability of very extreme values that we have not observed yet. That's the trick that we're going to do. Now, before we go there, we need to come with, we need to introduce some definitions. The relationship between cumulative probability, F, that we already saw. So the probability that what we use the symbol Y here for the maximum values. So if Z are the original series, then Y is the maximum values. So we have the probability that Y is smaller than a certain value. That's the cumulative probability distribution. We already saw that one in the previous talks. But we can also take the exceedance probability, the probability that it's larger than a certain value. And obviously that can be obtained from the cumulative probability by subtracting it from 1, right? Because the probability something is either larger than Y or it's smaller and equal to Y. So those probabilities have to add up to 1. And therefore the exceedance probability is 1 minus the cumulative probability. And then we have the return period. So that's the average number of years between two consecutive events. Again, it's the average. So basically, if the return period is 5,000 years, it means that on average, the event occurs once every 5,000 years. But it doesn't mean that it can happen this year and the year after. It can still happen with a certain probability. It's an average. So if we would, suppose the recurrence probability or return period, recurrence time would be 100 years, and we would measure 10,000 years, we would probably have close to 100 events. But they are not exactly 100 years apart. They can be all over the place. Actually, they're random in that period. But the average time between two consecutive events is 100 years. And that can be calculated by 1 minus the exceedance probability, or 1 divided by 1 over the exceedance probability, or 1 divided by 1 minus the cumulative probability. Yeah, again, I want to stress, it's really important that a return period doesn't say anything about an actual number of years between two consecutive flood events. It only says that on average a flood of a given size occurs so many years. Yeah. Now these things are easy to calculate. This is from Excel. This is also what we're going to do next next practical. So what you do is you take all your data in your, these are the Rhine discharge, and there's a function for that in Excel. You rank them from small to large. Then you give them a rank number. Yeah, these are 116 years of, or this is 118 years of data. And then the cumulative probability is the rank divided by n plus 1, so the number of years plus 1. As you can see, and then the exceedance probability That's the next column is 1 minus that number, and then the return period is 1 divided by that number. So we order it, we add a rank number, we calculate the rank number divided by n plus 1. We have a column that is 1 minus this column, and then we have a column that is 1 divided by that column. Yeah? So this is how that's done. Now, of course, that can also be done in R. This is how it's done in R. Then it's a so-called data frame in R. That's a certain structure. We end up with a data frame that has two columns, a time and discharge. We can rank it, calculate the rank number, and we can add actually columns to that data frame until we have the return periods. And then we can plot one against the other, right? Now, this is a plot, in this case in R, where we plotted the return period, dus this column, against Q. Yeah. Now you can see that the largest number we have 118 years or 117 years of data, and the largest return period that we can have is this one here. So that's 118 years. That's the largest one that we can have. Oh no, we have 116 years of data, sorry, and the largest one is 117 years. But what if I want to design a dike or a levee for the river that floods only once every 500 years? What am I gonna do? Yeah. So I'm gonna have to somehow extrapolate that, as you can see. So there's quite an extrapolation. Or even further, for instance, for sea dikes, then you know the return period may be 1 every 5,000 or even once every 10,000 years. So you see there's an enormous extrapolation that we need to do. So what do we do to extrapolate? Well, we assume that we already saw, we assume that the outcomes of the maxima that we observed are all draws from the same underlying probability distribution function. So they are identically distributed and come from the same probability distribution function, therefore, and they are random. Yeah. So what we do is we try to find this probability distribution, fit it to the data, and then use that probability distribution to extrapolate it to find the probabilities that certain very large values occur. This is what we're going to do. Now the question then is, what type of probability do we need? The distribution do we need? Well, from the box plots we already saw that a Gaussian distribution would not be very successful because we have an extremely long tail. So there are quite a number of very high ones that fall outside the normal years. So you have many years with average values and then just a few that are much, much higher than the average. So we need a very skewed distribution. And the workhorse for that, for maxima, is the Gumbel distribution. That's the one that has been used mostly. So the probability density function of that looks like this. It is b times e to the power of minus b y minus a times e to the power of minus e minus b y minus a. The cumulative probability distribution function looks a little bit more well, understandable. It's a double exponential, as you can see. So exponential of a minus exponential of minus b y minus a. Yeah. So this gives you the probability that the maximum is smaller than a given value of y. And as you can see, it has two parameters. A location parameter, which is comparable to the mean. So this is where the center of mass is of the Gumbel distribution. And there's a parameter that tells you something about the spread of the distribution, comparable to the standard deviation. And that's the scale parameter. where b is smaller than is larger than 0, and usually we work with 1 over b as the scale parameter. Okay. So just some examples you can see. So this is A0 and B1. This is A4 and B1. Yeah. And this is A4 and B is 0.5. Yeah. You can see the larger the larger 1 over b, so 1 over b is here 1 and the other one is 2. The more spread, the more spread there is in the maximum. Now, why the Gumbel distribution? Well, there's a theoretical reason actually why the Gumbel distribution should fit the extremes, and this can be derived from the actually it's derived for a Gaussian distribution for an exponential distribution. I think in the reader, but for any of those distributions, be it exponential, Gaussian, log Gaussian, gamma, logistic, Gumbel, you can actually prove that if you take maxima values from any independent set of outcomes of any of those distributions, and you take the maximum values of that, they all follow a Gumbel distribution. So there's a theoretical foundation why maxima should follow a Gumbel distribution. Now, one of the things that would be interesting, one of the things that would be handy to work on is the so-called Gumbel score. So we take the cumulative distribution, we take its national logarithm. Note we mention here by log we take national logarithm. I use log because that's also used in R. And minus the log of that, and take again the logarithm of that, and minus that. That gives you the so-called Gumbel score. And the Gumbel score is actually on a scale from minus infinity to plus infinity, depending on the size of f. If f is very small, it goes to minus infinity. If f is close to 1, it goes to plus infinity. Yeah. So, what is the rationale behind this Gumbel score? Why is it? Why does it? And actually, you can write the cumulative probability as e to the power of minus e to the power of minus g. Yeah? So, why is that? Well, this is the cumulative probability distribution. Well, we take 1 times the log on both sides, then we and then minus multiply times minus 1. So the logarithm of this exponential disappears, and we take the minus of that. So this minus disappears as well, and we end up with e to the power of minus b y minus a. Then we take again the logarithm of that result. So if we take again the logarithm of this, we get b minus b y minus a, and then multiply times minus 1, we get b times y minus a. Now we rework this thing to make sure that b goes to that side and the a goes to the other side, and you can see that the maximum is equal to a plus 1 minus b times the Gumbel, the g variable, yeah, the Gumbel variate. Now this makes sense because you can see that our maximum is determined by the size of g, which is the size of the probability. So the larger the larger f, the more extreme the value, the larger g, and it has a location parameter and a scale parameter 1 over b. And the other thing is that if we plot y against g, we get a straight line, and the intercept is equal to a, and the slope is equal to 1 over b. So that's quite handy. Yeah. So how is that done in practice? We saw we can first, from our data, we calculate the rank. We divide by n, the rank by n plus 1. We get an estimate of the cumulative probability. This is the exceedance probability, this is the return period, and we can also calculate from this guy here the Gumbel variate. So that's done here. We already saw FPT, but we can also get the Gumbel variate. You see the Gumbel variate here. And then we can plot the Gumbel variate, this one, against Q. Yeah. So that's done here, and you can see indeed it more or less is on a straight line. Not exactly, but it's quite okay. So this is your Gumbel score, and this is Q. Now, because this is now on a straight line, it's actually quite easy to fit this straight line and then extrapolate it. Yeah. So how is that done? So if we extrapolate it, we can also add the return levels. So we can actually add the return levels on the axis. Now, how do we get from the Gumbel score back to the return levels? Well, of course, we saw that T is 1 over P, is 1 over 1 minus F. So if you reverse this thing, we can write F as a function of T as 1 minus 1 over T, as you can see. Because we bring this one to that side, that to that side. So we get 1 minus F is 1 divided by 1 over T. So F is 1 minus 1 over T. We substitute this into the definition of the Gumbel variate. So we get this one. And we can revert this by taking exponentials. An exponential of a log, then both disappear, right? And we end up with a relationship between the Gumbel score and the return period. So this is how we can calculate for different Gumbel scores the associated return period. Now, then we can fit the line to it. And of course, we can extrapolate the line if we want to larger ones and get an idea of, for instance, this is the once in 100 return period of the Rhine, which is 13,650 cubic meters per second. So that occurs on average once every century. Yeah. Well, and it has occurred actually only once in the 20th century, as we saw from our time series. This is, by the way, coincidence, because it could have occurred 2 or 3 times also, or none. Yeah, because it's the average number of times it occurs in a certain time period. So, now, how do we fit the Gumbel line? How is that done? Yeah. Well, you can do it by hand. You can use so-called method of moments. That's one of my favorites because it's so simple, and it's actually the one that I will also most likely ask you at the exam to do. Then there's using regression. Well, we will do that in R also in the next practical. And more fancy is even gives a little bit better fit for the parameters, so-called maximum likelihood estimation. So this is how it was done by hand, actually. This is how I learned it at school when I was, or at university when I studied hydrology in the early 1980s. We have this so-called Gumbel paper. So what is here on this axis, this axis is linear in the Gumbel deviate, but then they translated the Gumbel deviate to return periods. And so what they plot here is the return periods, as you can see. So you calculate, so going back to the previous, we calculate return periods like this from our data. And then once we have this return period, we plot them on the Gumbel paper. Yeah? And the return periods are here on this very strange axis, because this is a double logarithmic scale. And here, this is a linear scale. We plot the discharges, and then we can actually fit by hand, we can fit a line through it, and for instance get the once every 200 meter the once every 200 year flood by extrapolation, or the once every 500 year flood. Yeah. So this is how it was done traditionally before the advent of the personal computer. There were also mathematical ways of doing it, making use of the properties of the Gumbel variable. Because if y is distributed according to the Gumbel distribution, then, and we know the time or the scale and the location parameter, a and 1 is over b, we can do, one can derive theoretically that this is an equation for the mean and this is an equation for the variance. Now we can revert those equations, first this one, to calculate, so what we do is we calculate the mean and the variance directly from our data. So we don't have to order them or anything, we just calculate from all the maxima that we have, the 116 data, we calculate the mean and the variance. We estimate it. We put with the variance, from the variance we can get 1 over b, and once we have 1 over b, we can calculate the location parameter, and from this we have 1 over b and a very quickly, without having to fit a line. Now this is a very simple and straight way of doing it. The disadvantage is that if there are some errors, if there's quite some noise in your data, then these estimators are quite uncertain. So you get quite a large uncertainty in the values of 1 over b and a if you do this. But it's very quick. Now then there is regression that can be done in Excel, but it can also be done in R directly. So as you can see, this line is fitted through all these data here and then extrapolated to get, for instance, the once in every 500 year flood for the Rhine. That has not been measured yet, not in our, at least not in our times, since the beginning of the measurements in the 1900s. It probably occurred before that, but we haven't observed it directly, and that's over 6,000, close to 6,500 cubic meters per day, per second. Sorry. Yeah. And yeah, we can use this to extrapolate, and even further. This is how we get the. This is even extrapolated until 2500 and 1250, and this 1250 here, yeah, this is actually the design flood for the river dikes in most of the river area in the Netherlands. So the design flood is 18,000 cubic meters per second. So you just calculate it by finding the correct value of G that belongs to that return period. Once you have that G, you can calculate the associated flood. So that can also be done numerically. Yeah? So once we have fitted the parameters, suppose we have a location parameter of 5593 and a scale parameter 1 over b equal to 1752. Yeah. Now you ask yourself, what is the once in every 1250 year flood that we need to design our dike? Well, this is 1 minus 1 over 1250, taking minus log of that, taking the minus log of that, and we end up with a Gumbel variate of 7.1305. Then we plug it into this equation with this value of A and this value of 1 over B. So the design flood that occurs on average once every 1250 years is equal to the location parameter plus the 1 over B, the scale parameter times the parameter, the value of G, and that's 18,000 and a little bit of cubic meters per second. Yeah. So so that's simple. So what is the method? You take the maxima for every year. You either estimate A and B from method of moments, or from a or for plotting it on a straight line and with regression. You fit A and 1 over B, and once you have that, you can calculate the from any return period. You can use these equations to calculate what the design flood is that belongs to that. And once you have the design flood, obviously you can calculate what the water height is that belongs to that, and then you know how high your dike should be. So this is how it's done. Now there's an issue here, and that's uncertainty, because as you can see, these data are not nicely on one line. So suppose I take a subset of these data, a random subset, there's a little bit smaller of the data, and fit again this line. You can see I can fit many different lines to that. Those are all alternative lines, and they're just a little bit different because of the fact that these data have some noise around that line. So there's an error in the location, and there's an error in the slope, which is the 1 over B. Now, if you use a regression, you can calculate, you don't have to do this fitting of the lines every time. You can actually calculate a 95% prediction interval for each return period. And that includes the uncertainty about A, the uncertainty about 1 over B, and of course also the residual, the fact that all these data are not lying exactly on this straight line, but they have some deviation. So these three sources of error in the slope, location, and the deviation from the individual data from the line, they are taken into account to calculate this 95% prediction interval. So this can be done automatically, and we see that also in a practical when you use R. But if you use the method of moments, there's actually an approximate equation that once you have calculated the return period and there's a certain G associated with that, and you also have A and B from the method of moments, then this is a measure of the prediction error variance, and this gives you the prediction 95, an approximate 95% prediction interval for that particular return period. I would say again that this variance here, you see, this is not the variance of y itself, but y hat, so of the prediction error. So if I calculate what the design flood is for a certain return period, then that design flood has a certain value, but it also has a confidence interval around it, and that's an error. It's not the variance of y itself from your data. That's another variance. That's the variance of all the maxima that could occur for every year, not for a given value of for a given value of t. So that's a different variance. That's an error that many always make. Okay. Now this is all a straight line, but you could also say, well, it's not necessarily the case that these are all on a straight line. Maybe a curved line is better. So there's a so-called generalized extreme value distribution, or GEV distribution, that can be fitted to a maxima that is often used much more than Gumbel these days. And it's actually a generalization where the Gumbel is just one particular form of that. If we take, so it has an additional parameter, a shape parameter. If we take the shape parameter equal to 0, this distribution is exactly the same as the Gumbel distribution. So the Gumbel distribution is nothing more than a GEV with a shape parameter of 0. If the shape parameter is smaller than 0, like here is negative, then the maximum values are actually a little bit less than you would think based on a straight line. You can see that here, right, on this one. You see they're all below the straight line. So we actually overestimate a little bit the probability of many of the extremes in this case. So then you would typically fit a shape parameter that is negative. If the shape parameter is positive, then the data starts to deviate from the straight line like this, which means that the probabilities of the very high floods are underestimated by a straight line, by the Gumbel distribution, and we have a positive shape parameter. Now again, the R software either fit these lines are not longer fitted by regression, but they're fitted by the so-called method. They're fitted by maximum likelihood estimators. They're a little bit more robust when it comes to noise in your data, and you get therefore more accurate parameters. So your location, scale, and shape parameter will be more accurately estimated. And it also gives you the 95% prediction intervals, which, as you can see, are no longer symmetrical. Yeah. So they're a little bit skewed to the right, as you can see, these prediction error intervals. So what we typically say, we fit a distribution that the 500-year flood is equal to 13,420. Plus of, but it has a 95% confidence interval, say between 11,500 and what is it, 15,000 or something. Yeah? Okay, so this is actually everything I would like to tell you about how to fit a Gumbel distribution. Just to repeat itself, you have to we select the maxima, we calculate from F, we calculate rank numbers, we calculate F, we calculate P, we calculate T, and we calculate G, and with these rows statistics we can fit a Gumbel line either by method of moments, regression, or maximum likelihood. And we can use that line to extrapolate to find design floods of very high probabilities. Say ones that occur once every 500, 5,000, 1,250 years, etc. Okay, just some other stuff. We saw that the expected number of, what is the expected number of T-year events in N years? Yeah. So suppose, what is the probability? Yeah. That the 100-year event occurs in the next 30 years. Yeah? Well, that can be calculated by N is then 30, T is 100, so that probability is 0.3. Yeah? So this is the expected, sorry, it's not a probability, but that is the expected number of T-year events. The actual number of events obeys a binomial distribution. Yeah. So the probability that we have n events of size yt in n years is given by this equation. N over n is the number of times that we can fit a number of years in a larger number of years. Yeah. So number of events in a number of years. Yeah. This is the exceedance probability, and this is the this is the so-called binomial distribution. Just to give an example to make it a little bit more tangible. For instance, what is the probability that we have exactly one event, y100, in 10 years time? Yeah. Well, that is calculated as 10 over 1. I will just give you an example how to calculate that later on, but 10 over 1, yeah, multiplied times 0.01, because that's the exceedance probability of a 100-year event. That P is 1 over T, which is 0.01, occurring exactly one time, so little n is 1, and then times the probability that it doesn't occur 9 times in those 10 years. So that's 1 minus 0.01, 0.99 to the power of 9. So that is 0.0914. The probability of one or more events in 10 years is actually equal to 1 minus, so this is good to remember, this is exactly one event in 10 years, and this is one or more events. So that's the probability it occurs once, plus the probability it occurs twice, plus the probability it occurs thrice, etc., until the adding also the probability that it occurs 10 times in 10 years, which is highly unlikely, obviously. So that probability is, of course, a little larger than that it occurs exactly once. So that's 1 minus the probability of no events is 1 minus 0.99 to the power of 10 is 0.0956. Yeah. Definition of n above n, yeah. So that's the number of times, the number of possibilities, or so-called permutations, that we can fit a lowercase n events in n years, yeah. And that is actually by definition equal to n factorial divided by n factorial times n minus smaller n case factorial. Now, if you have a graphical calculator, you can actually get this directly. If you don't, then there's always a trick to calculate this. For instance, if you want to know the number of times that 3 events fits in, by the way, this is equal to n times n minus 1 times n minus 2 times etc. That's how it is. So if you want to calculate this one, actually this is equal to 10 times 9 times 8 times 7 times 1, eh? And then we divide it by so this one, so that is 3, so that's 3 times 2 times 1, and then times, and then n minus n factorial, so that is 7 times 6 times 5 times 1. Yeah. Now the cool thing is that we can actually get rid of this part and this part because they cancel, as you can see. They are the same. Yeah. So we end up with 10 times 9 times 8 divided by 6. Yeah. So this is really doable. So that is actually 10 times 9 times 8 divided by 6. So that's 120, yeah? So there's 120 ways to fit 3 years in 3 events in 3 events in 10 years, yeah. Okay. Then another thing, just to give you a perspective on, that's also interesting, on the 1200 years flood. Yeah, if you live in the river area, then the design is the design is the T is 1250 years. Yeah, so the dike is high enough to withhold any flood larger than, well, in this case, Q is about 18,000 cubic meters per second, right? Now, if you think, okay, well, you know, I'm never gonna experience a flood like that in my lifetime. It's gonna the probability is gonna be quite low. Well, now you guys are on average now, say 20. Suppose you well, suppose you are in a generation that probably has on average still 75 years to live. Yeah. So what is the probability that a flood that is larger than the 1250-year design flood occurs in 75 years? Yeah. Well, P, little p is once over 1250, and that is equal to, let me calculate that one. Once, right? So that is, sorry, how many zeros? 3. Is 0.0008, so it seems to be very small. So that's the probability that it occurs in any given year. Yeah? Now, what's the probability that it occurs, that any of those floods or larger occurs in 75 years? That is 1 minus the probability of no floods. Yeah? In 75 years. So that's 1 minus what's the probability of no floods in 75 years in a row. So that is 1 minus 0.9992, I guess. But then to the power of 75. Yeah. Let me check if I do it correctly. Yeah. Okay. And what is that? What does it end up to? So if I do this one to the power of 75, minus plus 1 is, so it ends up with a probability of 0.058 approximately. So you can see, even though the probability of that, the average number of years between a flood that floods basically is larger than the large river dikes is very small, that probability. That's so occurs once every 1250 years. The probability that a flood of that or higher that will flood the lands occurs in 75 years, which is the rest of your average remainder of your guys' lifetime, is still 6%. So that's not so very small, actually. So that gives you an appreciation that this is an average recurrent period or an average probability for a given year. But it doesn't mean that it cannot occur at all. We can also get the expected number of years until the next year event. Yeah. And that's follows a geometric distribution. Yeah. So given that we live now, what's the probability that the event occurs in 1 year, 2 years, 3 years, and so on? And of course, the longer the waiting time, the higher the probability becomes that it will occur in any of those years, obviously. Okay, then finally, you may also be interested in low flows. Well, there is a special distribution that sometimes is used for minimum value, is the Weibull distribution, but you sit with these low flows, you always have a problem that they have to be larger than 0. So sometimes people take either the negative of Z, or what's even better, you take 1 over Z. So that gives you the, so then you take your minimum values, you do 1 over the minimum value, and then you analyze them as if they are maximum values, and then you can, after your analysis, you can then get them back, revert back to minimum later on. Yeah, that's one way of dealing with minimum values. Now then finally we end up with, we have to check whether the maxima values are, one of the assumptions is that they are independent random variables between consecutive years. They are completely random, and you have to be sure that there's no trend. Well, how do you fit a trend? Well, this is 2 series of maximum values. Actually, the right one is from the Rhine, and this is another one. And as you can see, this is fitted with R. We just fit a regression line through it directly. Yeah, so they are not ordered now. They are just, this is time. This is not a G. This is not the G variable, but this is. So what you can see is that in this case, you get the estimates here. This is the intercept of that line, and this is the slope. The time is the, this is a regression, and this is the explanatory variable. So this is your slope. This is a slope of 0.06, yeah, and this is the standard deviation of the slope. And if the slope plus or minus 2 times the standard deviation is different from 0, it's a significant slope. Yeah, you can also calculate the p-value. That is the probability that this slope occurs randomly. And if this probability is large, then it's not significant. But in this case, you can see this probability is larger than that is. In this case, you can see that the slope plus or minus 2 times the standard deviation of the slope is different from 0. So it doesn't contain 0. So it's significantly different from 0. And also the probability is smaller than 0.05. So it's a significant slope here. So here there's a trend in your data in this case. Here there's no significant trend, and here is a trend. Now if you apply this to the maxima of the Rhine, you would actually see a small but significant positive slope. And that has to do with climate change, probably, is that precipitation has increased, and therefore discharge has slightly increased as well. So you actually have to remove that trend before you do the analysis. And then finally, there are tests. This is one, is von Neumann's ratio test. There are many other tests to test whether the time series of data are independent.